Okay, now we're going to talk about acronyms, and this time we're going to talk about both the HVZ and the BV, aka the Baeyer-Villiger. Very cool stuff. Alright, so the Hell-Volhard-Zelinsky, that's a super cool reaction just because of its name. But it's also pretty cool because it allows us to carry out some chemistry that otherwise is simply inaccessible, as we'll see toward the end of this mini lecture. The problem is that if I wanted to carry out some kind of reaction to synthesize this alpha-substituted carboxylic acid, the logical disconnection would be to think about this guy as a nucleophile. After all, sodium cyanide, potassium cyanide, that should be added as a nucleophile. Well, but the thing is then, if I'm going to try that, that means somehow or other I'd need to make this an electrophilic carbon, which makes zero sense at all, because what we know about alpha carbons is that they can be deprotonated to make enolates. And of course right now you should probably be able to see what the real issue is. How can I possibly have an enolate in the presence of that acidic carbon? Of that acidic hydrogen? No, if I try to deprotonate my carboxylic acid, well, the first hydrogen that's going to get taken off is this guy. Alright, so that's going to be removed. I get a negative charge there. Then I'm pretty much dead in the water, because there's really not going to be a good way to take that hydrogen off too. That dianion is too unstable. It's too difficult to carry out that deprotonation. Phooey. So, trying to go basically from here, boom, to my target, it's just not really feasible because I can't make that alpha bromo acid. So what can I do? Well, I can do the HVZ, the Hell-Volhard-Zelinsky reaction. And I'm just going to show you what that reaction is by showing you the mechanism, and you will see how that solves all our problems. So basically you take your carboxylic acid and you treat it with phosphorus tribromide or phosphorus trichloride, and what you would expect is that your nucleophile would react with that phosphorus tribromide electrophile, and this is also a good review of the last mini lecture because this is showing you how these phosphorus trihalides can convert your acid to the acid chloride, or in this case we'll see the acid bromide. So reaction of the nucleophilic oxygen with the electrophilic phosphorus gives us the intermediate shown. What happens next? Well, you know what happens next. We're going to deprotonate that guy. So, sure enough, the Br minus that got kicked out can come over here and pluck off that hydrogen. And that gives me this intermediate. And what you should see about that intermediate is that that's really a pretty good leaving group. So, in the presence of another bromide, well, don't worry, our bromide, we got bromides aplenty here. Br minus is going to attack, let's see, an electrophile. What electrophile might that be? That electrophile. So that gives you the tetrahedral intermediate, and of course you know what happens then. We're going to pop back down, make our CO double bond, and kick out this fantastic leaving group. Remember, the phosphorus-oxygen bond is a rock. When you start thinking about the Earth, for example, there are so many phosphates on this planet, and that is because of the thermodynamic sink that is the phosphorus-oxygen bond. So, there you go. We now have an acid bromide. And because we have an acid bromide, we don't have an acidic hydrogen there anymore. So, now I can move right ahead to my alpha brominated acid bromide, react it with whatever I darn well please. I think we'll just, okay, we'll go ahead and add our NaCN, SN2, kicks that bromide out, and then hydrolysis of the acid bromide takes us right to where we wanted to go in the first place. So, it's the Hell-Volhard-Zelinsky mechanism that allows us to basically make that particular molecule. It allows for you to functionalize carboxylic acids at the alpha position. Okay, and don't forget, when I say alpha position, I mean that carbon right next door to the CO double bond. So that is fun and interesting mechanism in reaction number 1. Fun, interesting, and super reaction number 2 is the Baeyer-Villiger. So the Hell-Volhard-Zelinsky solved the problem. What's so great about the BV? It's just the coolest reaction ever. Because basically, you take a peroxy acid, and it's serious tinker toy chemistry. Just think about this, guys, and for a second as a model set. All you're doing is just boop, popping open that bond and sliding an oxygen in there. That's pretty amazing. So, how in the world can that happen? Well, it's a great opportunity for review. First of all, do you remember hydroboration? Remember hydroboration? Oops. I always forget to change back there. Hydroboration is our friendly BH3 and then basic conditions, hydrogen peroxide and water, to give me the anti-Markovnikov alcohol. So I want you to focus on the workup right now. So in the reaction, you will recall, right? You will recall the most dreaded words in an organic chemistry class. You will recall that the trialkylborane adds in one swell FOUP the hydrogen adds to the more substituted carbon, the boron adds to the less substituted carbon. This happens 3 times. So here is your trialkylborane. Upon formation of the trialkylborane, then you do your workup, and under basic conditions what you have is the peroxy anion. Well, what electrophile is present? Well, the electrophile that's present is absolutely, positively your boron. That's supposed to be a p orbital, and it's an empty p orbital. It's a pretty bad picture of a p orbital, but nonetheless, it makes your boron electrophilic. So, the nucleophilic peroxy anion zips right in there. There's no leaving group to kick out. It just makes a new bond between the O- and the boron by dumping into that empty p orbital. So here is your borate. Okay, now what? So remember that boron has this crazy tug-of-war. It's happy when it's neutral, but it's sad when it's anionic. But it's sad when it only has 6 electrons, and it's happy when it has 8. It's kind of a schizophrenic molecule. So, in order to move forward, basically what we see in the hydroboration mechanism is that your alkyl groups have this fantastic driving force for doing a 1-2 shift, a migration here, breaking the super weak oxygen-oxygen cleavage. Okay, so you remember that's always the driving force. Those oxygen-oxygen bonds are super weak, and we're making a nice strong carbon-oxygen bond in this shift. So we're going to see the same kind of chemistry in the Baeyer-Villiger. So I said the reagent is the peroxyanion, is a peroxy acid. So under basic conditions, this is our nucleophile. It adds to the electrophilic carbonyl. Well, there's the tetrahedral intermediate, just as you would expect. Then what? Well, draw the parallel. Basically, we've got the same oxygen-oxygen bond that wants to break, and we've got the same alkyl group that can shift. So I'm going to shift this alkyl group all the way over. Ooh, I'm running out of room here. To that oxygen to make a new intermediate. And that intermediate is going to look like this. And I'm going to draw it nice and big here. Okay, so I'm not breaking that bond, but I am moving. This is the bond that migrated, and in so doing I kicked out that good leaving group. So I'm going to try and erase this part over here and make this a little clearer. So this bond shifts over to the oxygen and breaks that oxygen-oxygen bond. What's missing on the right is that in so doing it leaves a carbocation on that carbon, and needless to say we can draw a nice resonance contributor for this. And that should take us to our product. Just deprotonate it. Let's count carbons to make sure we didn't screw up. 1, 2, 3, 4, 5, 6. Yep, we still have 6 carbons, but we slid that oxygen in there just by a 1-2 shift and breaking the oxygen-oxygen bond just like we saw in the hydroboration workup. Pretty nifty. Okay, so we'll wrap this up by looking at a couple of examples of this chemistry and synthesis. So let's say I want to go from methylcyclopentanone to that molecule? Well, that's pretty miraculous. Obviously, it means breaking a carbon-carbon bond. We should always start, if we have a starting material, by counting carbons, and we know this is a C6. So what do we have over here? 1, 2, 3, 4, 5, 6. Oh. So we haven't lost or gained any carbons. Well, we can make some assumptions. Maybe that's the same carbon. If that's the same carbon, then if this is 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, somehow or other it would appear that we are getting an oxygen right there. there you go. If I could just do a Baeyer-Villiger on that ketone, I would be able to then add what? I want to ring open this ester. I want to hydrolyze this ester into the alcohol and the acid. So that's just hydrolysis. And the Baeyer-Villiger is just a peroxy acid. It could even be MCPBA. And in fact, it usually is. So one thing you should notice here is that in this example, it is not symmetric. So we could get that. We could get insertion of the oxygen on this side or on this side. And those are two wildly different products. So it is in fact the more substituted carbon that is more likely to migrate in that 1-2 shift. All right, one more example. This is an example from the recent literature. They needed to synthesize this guy. It's a natural product. This is the starting material, actually, the reaction they needed to carry out. They wanted to convert it to the unsaturated amide, the conjugated unsaturated amide. And that's a problem because just like acids, this particular amide has an acidic hydrogen. Because of that, if I try to make the enolate, it's not going to work because deprotonation of this guy gives me an anion there, and then I can't make the enolate. So how did they do it? HVZ, the Hell-Volhard-Zelinsky reaction. They managed to make the alpha iodo compound, which they then used to undergo an elimination reaction. So I don't know specifically what base they used, but a base they used, and they were able to put in that double bond. So these are chemistry reactions that are used every day in all manner of situations, from biochem to material science. And they're cool. But you know what? They're all electrophiles and nucleophiles, so you can keep them straight in your head, I promise. But let me just give you a little joke that will help you understand how you can approach organic chemistry. And I share this joke in the spirit of, it's spring training time. Baseball is in the air. So a little boy was overheard talking to himself as he strutted through his backyard carrying a ball and bat and shouting, "I'm the greatest hitter in the world." Then he tossed the ball into the air, swung at it, and missed. "Strike one," he yelled. But he was undaunted, so he picked up the ball and repeated, "I'm the greatest hitter in the world." Tossed the ball up when it came down again, swung and missed. "Strike two," he called. So he paused, looked at the ball, spit on his hands, really got a good grip on the bat, said to himself one more time, "I'm the greatest hitter in the world." And again he tossed up the ball, swung at it, and completely missed. Strike three. Now you might think the poor guy would be a little disheartened by now, but no. What did he say? "Wow," he exclaimed, "I'm the greatest pitcher in the world." So there you go. It's all in your perspective. So, with that in mind, tackle some Chapter 21 problems, and we will see you in class.